morning. Okay, let's get back to nuclear chemistry. We had left off talking about bombardment equations, which you balance in the same way that you would balance a decay equation. You just make sure that the top numbers on both sides equal each other and the bottom numbers equal each other. So when measuring radiation, because different things give off different amounts of radiation, some things give off a really small amount of radiation that's relatively harmless. There's always sort of like a background level of radiation that we're exposed to anyway. But then there are certain things that have higher levels of radiation, so we can measure them using a Geiger counter. So here's a Geiger counter. It has some sort of cathode here that when gamma rays or beta rays, kind of more detrimental ones, hit this cathode, it will ping an electrical current, which will then move back towards some sort of meter or receiver, and then the receiver will indicate that there is radiation. Usually it's like a click sound. And the more clicks you get, the more radiation you have at your source. So some of the units for measuring radiation, we have the Curie for Marie Curie, who did a lot of research with her husband in radiation and radioactivity, and won a Nobel Prize. Also her daughter did as well. There's a movie about her, I think, I don't know if it's on Netflix or Amazon Prime, it's on one of them, but it was a decent movie. But the content was really interesting because it talked about her life. But anyway, so she did a lot of work with radiation. So they named a unit of radiation after her. What we classify a Curie as is the number of disintegrations that occur in 1 second for 1 gram of radium. So if we're looking at radioactive radium, we would see that it has 3.7 times 10 to the 10th disintegrations per second. So it's quite a few disintegrations. A Becquerel is the standard SI unit of radiation or radioactivity, and this is 1 disintegration per second. So this is much smaller than a Curie, right? If this is 1 disintegration per second, a Curie is 3.7 times 10 to the 10th disintegrations per second. A RAD, radiation absorbed dose, which measures the amount of radiation that you absorb by a gram of material. So body tissue, for instance. And then a gray is the SI unit for absorbed dose, defined as the joules of energy absorbed for 1 kilogram of body tissue. So if you're really, really close to a radiation source, your gray value is going to go up. You're absorbing more energy per kilogram of your body. The REM is another unit that we can use, which is radiation equivalent in humans. This measures the effects of radiation. So alpha particles don't penetrate the skin. We had said that earlier, that we can stop alpha particles with like a sheet of paper or even your skin. But if you were to eat something that contained alpha particles, it could do a lot of damage to the interior of your body. So don't eat alpha particles. You can help it. High energy radiation like beta particles and also protons and neutrons, they kind of get classified in that, travel through tissue and they can cause more damage than alpha particles. So you need something a little bit hardier to stop them. And then gamma rays are the most damaging, and they can travel through all sorts of different things and mess all sorts of stuff up, even on like a DNA level, tear your DNA apart. So units, all right, great. Move past this. We also have another thing called a sort of a unit that you can use for radiation sickness. And it's called an LD50, which is the amount of REM or amount of radiation that something could experience, and 50% of those life forms would die. Okay, so for instance, humans can experience about 500 REMs, and half of the people in that sample would die. Dogs are more sensitive to radiation. They can only experience 300. Rats are less sensitive. And then look at over here, insects, right? Like the cockroaches will rule the world. They can handle a large amount of radiation. Their biological material is just not as sensitive to it. Insects are even better than bacterium. All right, we can kind of skip over this. Okay, let's talk about half-life of a radioisotope. So here's the Dead Sea Scrolls, and they can actually calculate the specific age of it. How do they do that? Well, they look at a radioisotope in it, carbon-14, and they see how much of that radioisotope has decayed to its daughter isotope. So we think of carbon-14 or the radioactive isotope as the parent isotope. The parent isotope will decay to a daughter or a child isotope, which is the stable version. So let's look at iodine 131. After one half-life, iodine 131, well, the amount of radioactive has been cut in half. So half of it is iodine 131. You still have half radioactive. And then the other half is its daughter isotope or its stable child, which is xenon 131. What happens if we go through another half-life? If we go through another half-life, we don't cut half of the original, we cut half of whatever are at that step. So it would be half of half, right? So if there's half of the iodine 131 remaining, at the second half-life, a quarter of the original iodine 131 is remaining, and 2/3 is the daughter isotope. What happens if we go through 3 half-lives? We cut that third step in half, or we'll have, what do we have? Half, a quarter, an eighth of the original remaining. So each half-life will cut the previous amount in half. So let's say we started with 20 milligrams of this iodine 131, and we went through 3 half-lives. Well, in order to calculate how much of the radioactive stuff you have at the end, there are equations. Yes, if you've taken any like moderate level math class, you've probably used the equations for half-life. We aren't going to use the equations, okay? They're exponent equations. This is as advanced as it's gonna get. So you count how many half-lives there's been. This has been 1, 2, 3 half-lives. You take your original amount and you just keep dividing it by 2 until you cross as many half-lives as you've had. So I'd take 20 and I cut it in half to 10. I take 10, I cut it in a half to 5. I take 5 and I cut it in a half to 2.5, and you're done. Okay, that's gonna be the extent of our half-life calculations. If we had had 5 half-lives, I'd have to keep cutting this thing in half until we reached 5 half-lives. So this is what we call a decay curve. It means that we are literally watching our stable isotope decay down to, or rather our radioactive isotope decay down to the stable isotope. It's an exponential decay as well, meaning that it drops very quickly. So usually when we're using this to date something, after about 6 half-lives, it becomes somewhat inaccurate. So usually we don't use these past 5 or 6 half-lives. Looking at iodine 131, the half-life of this thing is 8 days. That's going to be unique to the material, okay? But it's consistent within the material. So iodine 131 will always decay at a half-life rate of 8 days. So half of it will be gone in 8 days. Half of that will be gone in another 8 days. Half of that will be gone in 24 days, so on and so on. So here are some of the half-lives for some common radioisotopes. Here are some of the naturally occurring ones. So carbon-14 has a half-life of 5,730 years. That's why they use carbon-14 to date like anthropologic things. So the Dead Sea Scrolls, they're going to use carbon-14 or a mummy or, you know, whatever, a pottery, because this age is really good to fall in the like thousands of years, right? We're not going to age the Dead Sea Scrolls using uranium-238. Why? Because it has a half-life of 4.5 times 10 to the 9th years, right? We're talking on scales of billions of years. This would be something that maybe we would want to age like the universe with, okay? And then radium-226, this would be another one that we could use anthropologically. That's on a good scale. Strontium-90, we could actually use that to age maybe even like on a single person's lifetime, right? Like the change, I don't know what you would use it for, but you could use it for something that we'd measure in a single generation or 2 generations. Here are some isotopes that they use in the medical field. So this is to map out, you know, like when you're getting all sorts of different readings, CT scans, all those sorts of things, the machinery has to read something. So they usually put a radioactive dye in your system. That dye, you don't want that in your system for the rest of your life. And they need it to decay fast so that they can give it to you in the morning, and by the afternoon, you're emitting radiation, right? So a lot of these are on a much smaller scale, half-life wise, right? We're talking, you know, the biggest here being 75 or 74 days, the quickest being, you know, 6 hours. And then these are all the different types of radiation that they're undergoing. So if we were to look at carbon-14, we're going to see it's emitting beta radiation. So how to use half-lives? Very simple for this class. State the given and needed quantities, write a plan to calculate the unknown quantity, write the half-life equality, and you can use it as a conversion factor, set up the problem. So let's say the radioactive isotope strontium-90 has one half-life of 38.1 years. So every time you go through one half-life, you pass 38.1 years. If a sample contains 36 milligrams of strontium-90, how many milligrams will remain after 152.4 years? So I don't particularly do these as conversion factors. You can if you want, but we've got quite a bit of information here, some of the given things. We're starting with 36 grams of a sample. We know how much time has actually passed, 152.4 years, right? And then we know that one half-life is 38.1 years. So I need to figure out how many half-lives have passed. If I can figure out how many half-lives have passed, then I can figure out how many times I need to cut my 36 in half, right? So if I have 152.4 years in total, well, I know one half-life is 38.1 years. This is setting it up in dimensional analysis. Otherwise, you can just take the 152.4 and divide it by 38.4, right? Because that's the total half-lives. You want to figure out how many individual half-lives you've had. So we've got 152.4. We're going to divide it by 38.1. 4 half-lives. You are not going to get tested on half-lives or quarter half-lives. That's when you'd need to use the equations, right? You're always going to have whole numbers. So 4 half-lives have occurred. Okay, well, if 4 half-lives have occurred, that means I need to take my original sample of 36 and I need to cut it in half. How many times? 4 times. Yep. So we're going to take 36 and I'm going to cut it in half. That gives me, oh my gosh, where is my brain today? 15, 16, 17, 18. I don't know where my brain is. All right, that's one half-life. Then I need to cut that in half and I get 2 half-lives, right? This is 9. Then I need to cut that in half, right? And that's 4.5. Then I need to cut that in half. 1, 2, 3, 4 half-lives. Gives us 2.25. So we just take the original sample and chop it in half until we get to the number of half-lives. So the remaining amount of strontium-90 should be 2.25 milligrams. So you figure out how many half-lives have occurred and then just cut in half that number of half-lives. That's going to be it. Doesn't have to get much scarier than that. Carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old and the half-life of carbon-14 is 5,730 years, what is the fraction of the half-life that has passed? And we don't need to worry about that. I'm not going to test you on that. Yeah. Okay, let's do this one. Let's have you do this one. The half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of iodine-123 is left after 26 hours? Okay. Okay, so looking at this one, we have our original sample, which is 64 milligrams. Need to figure out how many times I have to cut it in half, right? So a half-life is 13 hours and it's been a total of 26 hours. That means 2 half-lives have occurred. So I got to cut it in half twice. So I've got 64 milligrams. I'm going to cut it in half once to give me 32 milligrams. That's 1 half-life. And then I'm going to cut it in half again to give me what, the 16 milligrams? This is a second half-life. So B would be our answer, 16. If it had only been one half-life, that's where the 32 would have come in. If it had been, what, 3 half-lives, it would have been the 8 milligrams. That's it for half-lives. It's not going to get any more complicated than that. Medical applications for radioactivity. So again, there's all these really amazing scanners, different types of scanners, CT, PET, MRIs, and they all involve some sort of radioactive material. So radioactive isotopes with short half-lives are used in nuclear chemistry. The cells in the body don't differentiate between non-radioactive atoms and radioactive atoms. So what will happen is the cells will incorporate the radioactive material into it, and then it will emit radiation and give you an image of the organs. So that's how we can see soft tissue things inside the body, because X-rays don't see soft tissue, right? They only give us an examination of the bones. So again, here are some of the medical isotopes that they'll use. So after a radioisotope is ingested, the radiologist determines the level and location of radioactivity emitted. Some sort of scanner will move over the area and absorb gamma rays and beta rays. My husband was actually just talking about some of this, about the importance of investing in things like NASA. Like people are always like, why should we put money into NASA? We don't need to worry about going to the moon. We don't need to worry about going to Mars. We need to worry about, other issues. Well, an astrophysicist who worked on NASA discovered the MRI machine and the application for the MRI machine. And that, a doctor is probably not going to come up with that sort of technology. So it is important to be investing in all fields of science. We were literally just having this conversation last night. So one thing, a PET scan, if you've ever heard of a PET scan, why is it called a PET scan? It's a positron emission tomography. So they use positrons. We'll have like radioactive fluorine, and it will decay to oxygen, and it will give off a positron. And the machinery will detect the positrons and then form a computer-generated 3D image of the organ. So cool. Here's a PET or a PET scan of somebody's brain. They're looking at different regions, trying to diagnose Alzheimer's. So where they're seeing a lack of activity in the brain. So cool, not the Alzheimer's, but the technology. A CT scan is another imaging method that they'll use to scan brains, lungs, and hearts. And again, it does a similar thing, right? Where they can see where tumors are, and they can detect if there's fluids in this soft tissue. An MRI machine, magnetic resonance imaging. This does not involve X-ray radiation. It's the least invasive. It's based on absorption of energy when protons and hydrogen atoms are excited by a magnetic field. So the magnetic resonance is they will send a magnetic field through your body, excite hydrogens in your system, and then be able to convert what they're seeing into an image. Because they're sending you into a magnetic field, that's why you don't want to do MRIs if you have any sort of like metal in your system, or really just anything that's metallic that could be affected by a magnetic field. Here's an MRI of the pulmonary system, right? We've got the lungs and the heart. Okay, so this is which of the following radioisotopes is most likely to be used in nuclear medicine? I would say, the bottom two are going to be much more useful. This top one, way too long. By the, they're going to give you, if they gave you potassium 40, maybe there would start to be, there wouldn't even be enough decay by the end of your life, right? So they need something that's going to turn over much faster. So short half-lives we like. Okay, last little bit here, we're going to talk about nuclear fission and nuclear fusion. So in the 1930s, scientists started bombarding uranium-235, which is unstable, or is not unstable, but it is unstable, but it's large. But they started hitting it with neutrons. And what they discovered is that it would make the nucleus extremely unstable very quickly, and the nucleus would decay into 2 smaller nuclei, and then it would also decay into 3 new neutrons. All right, so I've got uranium, I hit it with a neutron, a high energy neutron, it becomes unstable and it breaks apart, and then it produces 3 new neutrons, and also a buttload of energy. These 3 neutrons are moving very, very fast. So what can those 3 neutrons do? Well, now they can hit other uraniums that are around, specifically 3 uraniums. So this is known as a chain reaction. So in nuclear fission, there's fission and there's fusion. Fission is what we currently have technology over. Fusion is what we're trying to gain technology of. That's like the technology of the stars. And it would give us a plethora of energy. But right now we are stuck with fission. So in nuclear fission, a large nucleus is hit or bombarded by a smaller particle, and it splits into several smaller nuclei, and then also some new neutrons, releasing a bunch of energy, which is known as atomic energy, the energy of the atom. And so Einstein worked on this in the early 1900s, finding that if you can split atoms, you can produce a lot of energy. When a neutron bombards specifically uranium-235, we get an unstable 236. It undergoes fission, splits. We get krypton-91 and barium-142. But the important thing is that 3 new neutrons that are high energy are created, and those can then move on to hit other uraniums. So we get something like this. Just 1 neutron, right? Let's say we have a jar of this uranium-235. 1 high energy neutron hitting that will cause a chain reaction where the reaction feeds itself. The more times that it undergoes a decay, the more neutrons there are to progress the reaction, and the more energy we get. So it sort of exponentially grows. This is what is happening in a nuclear bomb. This is what is happening in a nuclear power plant. That's why sort of once you start that reaction, you can't really stop it. It kind of has to play itself out. You can kind of control it, but if there's material there, if there's uranium there for a neutron to hit and you've got neutrons floating around, it will move forward. And then also the key thing here too is that there's energy on this side, right? We produce a lot of energy. I mean, that's why we're even doing this. That's why we dedicate all this money to nuclear energy and nuclear weapons, because it produces all of this energy. Now, the opposite of fission, well, sort of the opposite of fission, is fusion. Think to fuse something together. So in nuclear fusion, what you're going to do is actually take 2 smaller nuclei or 2 smaller atoms, and you're going to like try and glue them together or smush them together. So sort of traditionally, the fusion reaction, you can fuse all sorts of things, but This is kind of what we see happening inside a sun, or our sun, or the stars, is very light atoms, like usually it's just hydrogen, get smushed together to form helium. When it smushes together, it also will release a neutron, and then this produces a lot of energy, large amount of energy. It has to occur at very, very high temperatures. Very high temperatures. Okay, we're talking like 1,000,000 degrees Celsius. It occurs continuously in the sun and stars to produce a lot of energy. I mean, think how much energy the sun is producing, how far away we are, and it warms us. It runs our planet. So the amount of energy that you could get off of a nuclear reaction is immense. The other thing that's really cool about fusion is look at what's produced. Here we have 2 hydrogens. I mean, hydrogen is something you can get out of water. If you could have a couple drops of water and take the hydrogens off of it, smush them together, and your product is helium, which is an inert gas and a bunch of energy, as opposed to what you have going on in a fission reaction. In a fission reaction, what are your byproducts? Radioactive waste. You still get a lot of energy, but then you have all that radioactive waste to deal with. Fusion is, sometimes they refer to it as clean, like clean energy, the clean energy. It would solve all of our problems if we could figure out how to harness this. Why haven't we harnessed it yet? Because it requires extremely high temperatures and very, very pressurized environments. They're able to make fusion happen in these funky things called, what are they called? A torus, I believe, is the name of it. And they sort of spin these particles around, but it requires very unique situation. You need to be in a plasma environment. It's not something that you can just like strap to the back of your car, unfortunately, not right now at least. What stars will do is they will build off of what they have kind of fused or smushed together. So hydrogens come together to form helium. And then in very, very small quantities, it'll take helium and smush it together to form, maybe oxygen, and oxygens will get smushed together to form aluminum, and all of these heavier elements will form. So all of the elements in your body, all the carbon, all the nitrogen, some of these heavier things, were all formed in the belly of stars. It's very, very cool to think about. If we didn't have stars, we wouldn't have anything outside of hydrogen and maybe a little bit of helium. So here is a fusion reaction. Large amounts of energy are produced. It's much less waste. It isn't currently happening on a mass scale. So let's talk about whether it's fusion, whether it's fission, or I guess it could be both. So a nucleus splits. That is going to be fission. Right? Large amounts of energy are released. I mean, fission and fusion both produce a large amount of energy. Fusion can produce more energy, but that could be both. Small nuclei form larger nuclei. That's where we smoosh them together. That can really currently now only happen in a star. So that would be our fusion, or in a very specific lab setting. Hydrogen nuclei react with each other. That would be fusion. They react to form helium. And then several neutrons are released. That would be fission. So you want to be able to differentiate between fission and fusion. It'd be really cool if we had fusion, have access to a lot of energy, a lot of clean energy. But it's not happening right now. Maybe one of you all will discover it. More practical way of harnessing that. All right, so looking at this, supply the missing atomic symbol to complete this fission reaction. So fission, because we're splitting, right? Here's our uranium-235. It's getting knocked with a neutron. It's producing Te-137. and it's also producing 2 neutrons over here. So multiply these numbers by 2, figure out what is the mystery nuclei. Okay, so top values and bottom values need to equal each other. So we need to add both of these together, right? So it's not 235 on the starting side, it's actually 236. The bottom is 92. So that means on this side, everything needs to equal 236 as well. And everything on the bottom needs to equal 92. So we just subtract to get the missing thing. Now, this is, we should have 97 here and 40 on the bottom. This 2 applies to both numbers, okay? So it wouldn't just be 235 minus the 137 minus 1. It actually needs to be minus 2. So if you were at 98 here, it's because you didn't take into account that it was 2 neutrons. If you don't like it written like this, you could write it like this: 1, 0, n plus 1, 0, n. 2 of them, you have to subtract out both of those. And you also produce a lot of energy. All right, that's it for nuclear chemistry. Do I want to start solutions? I do. I'm going to start just a little bit of solutions. We will get out of here a couple minutes early, but looking forward. So next week we will be just working on solutions, and then it's spring break. Do note that for your lab, you have 2 parts, okay? You have the part that is in the lab manual, and then you also have this additional second part. Just submit all of it here. Submit both parts there. So it'll be a especially long lab. Okay, so chapter 9 is all on solutions, meaning, you know, things that are dissolved in something else. This woman who's undergoing dialysis is being administered a solution that contains water and different amounts of electrolytes. It's moving through her system, sort of flushing her system out to regulate and help her body remove waste, because she has some issues with her kidneys, which are the filters for our system. So as far as what a solution is, over here we've got a solution. Solutions are homogeneous or homogeneous mixtures of 2 or more substances. So you need to have something that is mixed together, not bonded together though. Forms when there is a sufficient attraction between a solute and a solvent. So the solute is what's being dissolved, the solvent's what's doing the dissolving. If those 2 things aren't somewhat attracted to each other, they won't mix. The solute will just sort of sit at the bottom. There are two components. The solvent is usually the thing that's present in the larger amount. The solute is present in the smaller amount. So like if I take salt and dissolve it in water, the solute would be the salt, the water would be the solvent, what's doing the dissolving. Solutes, so things that are getting dissolved, they can be liquids, gases, or solids. They are spread evenly throughout your solution. So the fact that these are homogeneous mixtures means that they are evenly mixed. The concentration will be consistent throughout. Mix with solvents so that the solute and the solvent have the same physical state. So if I take, for instance, a solid like salt and I dissolve it in water, the remaining material, the salt water, will be liquid, right? So the salt, which used to be a solid, now takes on the physical state of the solute. They both are in a liquid form. Same thing with like gases. For instance, if I have a can of pop, there's dissolved CO2 in it. The gas is taking on the physical state of the thing that's dissolved in the liquid. These things cannot be separated by filtration. So I can't take salt water and pour it through filter paper and pull the salt out, but I can separate it through a process known as evaporation. So I could put the salt water on a hot pan and evaporate all the water, and the salt would be left behind. The salt isn't going to evaporate. And once they are dissolved, they're not visible, but sometimes they can give a color change. So you may see that the material turns blue or has some sort of hue to it when it's got something dissolved in it. How about salt? Salt doesn't do anything, right? It doesn't change the color. It's you can't tell that it's in there. The only way you could really tell it's salt water is, I mean, there's a couple different ways, but the easiest way would be to take a sip of it. So here I've got copper 2 sulfate. Okay, and when copper 2 sulfate is in its solid form, these two things are linked together. Now, when I put this in water, it will dissolve, and what happens is that the copper and the sulfate ion will actually pull apart from each other and disperse throughout the whole solution. So it's not a unit of copper sulfate, it's actually little Cu plus 2 pluses and little SO4 2 minuses floating around. Types of solutes and solvents. So we can have gas-gas solutions. Air is an example of a gas-gas solution, oxygen and nitrogen mixed together evenly. You could have liquid solutions like gas in a liquid in a liquid, or solid in a liquid. We kind of went over gas in a liquid and solid in a liquid. A liquid in a liquid would be vinegar. Vinegar is acetic acid mixed with water. Also, like any hard alcohol you have is a liquid solution. It's not pure alcohol. It's usually diluted with water to get it to some sort of proof or concentration. And then we can also have solid mixtures, something like brass or steel. These are not, you can't find brass on the periodic chart, but you can find zinc and copper. So it's zinc and copper mixed together. Brass is carbon and iron mixed together. Why do they mix them together? Because then you get like complementary properties. So you can get some of the great properties of iron here with also some of the nice properties of carbon. So water is a solvent. Water is one of the most common solvents in nature. Sometimes it's called the universal solvent. It does a really great job of dissolving a whole lot of things. It's a polar molecule, remember? So it kind of sticks to itself, and it also likes to stick to other things that are polar. So there's actually a whole field of solutions that are situations where they're dissolved in water, and they're called aqueous solutions, aqueous for water. So we will spend a lot of time in that. Why do we get solutions sometimes and not other times? Like sometimes you pour two things together and they don't become a solution. Like if I took a bunch of copper pennies and I stuck them in a container of water, they're not going to become a solution. because there isn't enough attraction between the solute and the solvent. The solute, or what's being dissolved in the solvent, what's doing the dissolving, needs to have a pull or an attraction to each other. So likes will dissolve likes. This is sort of your rule of thumb when dissolving things. Polar things will dissolve polar things. Non-polar things will dissolve non-polar stuff. So water dissolves anything that is polar. You would need like something like cyclohexane or something non-polar to dissolve fatty oils and stuff like that. All right. Do I want to get into there? Let's see. I don't remember how quite long this is. And we'll do a little bit more. We'll call it. So if I have a solution with an ionic solute, and an ionic solute is some sort of salt, or it's a metal and a non-metal. Remember, ionic, metal, and non-metal. Our go-to example always is NaCl, but you could use something like MgOH2, all sorts of different things. But what happens here is that the NaCl, which is traditionally a solid, when it's dropped in water, it becomes aqueous. And it gets this little AQ, aqueous meaning it's dissolved. Not only does it become aqueous, it also breaks apart into separate ions. So it's no longer a solid chunk of NAs blocked with CLs, it's little Na pluses and little Cl minuses all floating around. The water has pulled at the charged particles. So the little oxygens on this side, because remember there's a dipole moment, the oxygens on this side will pull at the positive sodium, and the little hydrogens will pull at the negative chlorine and sort of pick them off of the salt. At some point though, your solution becomes saturated. There isn't enough water to pull all the particles apart if you've really dumped a lot of salt in there. So a polar molecule, compounds such as methanol, this thing here is methanol, and we're gonna learn more of these names later on, so don't stress too much about it, but what we can see here is that it's carbon, there's 3 hydrogens, and then there's 1 OH group. The OH group is what makes this thing polar. So it will dissolve in water. It forms an attraction between here. So here it says, just to simply identify which one is the solute in each of these solutions. So I'm combining 2 things together and I want to know which one's the solute and which one's the solvent. So if I take 2 grams of sugar and I put it in 100 milliliters of water, the sugar is the solute, the water is going to be the solvent. If I have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol, whatever is the lower amount is the solute, or what's getting dissolved. So the methyl alcohol in this case would be the solute. The ethyl alcohol would be the solvent. If I have 55 milliliters of water and 1.5 grams of sodium, the solid is always going to be the solute. So that's getting dissolved in the water. And then air, 200 milliliters of oxygen and 800 milliliters of nitrogen. The oxygen is actually dissolved in the nitrogen because the nitrogen is the majority component. So solute, solvent. When solid LiCl is added to water, it dissolves because the lithium ions are attracted to the oxygen, and this is just symbolizing the dipole moment of the oxygen atom, the negative charge it has. The chlorines are attracted to the positive hydrogen. So that goes back a couple chapters. Oh. If we look at these, which of the following would dissolve in water and why? So things that are polar are going to dissolve in water because water is polar. This first thing is definitely polar. It's very asymmetrical, not balanced. So this will dissolve in water. Gasoline, you don't know a whole lot about gasoline, but look, it gives us a little hint here that says it's nonpolar. So gasoline, we would expect that it wouldn't dissolve in water because it's nonpolar. This right here, this is a very balanced molecule, iodine as a diatomic. It looks like this. It's this bonded with this, and there are some other little dots floating around, but it's nice and symmetrical. So that means that this is nonpolar. Right, so this thing would not dissolve in water. And then HCl, hydrochloric acid, that's a polar molecule. We would expect that to dissolve. So it's a matter of, is it polar or nonpolar? And then really ionics, most of them dissolve in water. There are some that don't, but most of them do. All right, so we'll stop there. We'll go, we'll get into electrolytes and stuff next time. You should be good for your homework. The only thing is, again, there are 2 parts to your lab. First part is in the lab manual. Second part you will get off of Moodle, but submit both of them how you have been traditionally through the Moodle page. So you'll have quite a bit of pages to submit. Yeah, that's all I've got. So really have a good weekend. There should be some nice weather. Let me know if you have any individual questions. Otherwise, I will see you next week for 1 week until we get spring break. Bye, guys.